So welcome also from my side for this evening session. So my name is Christoph Jung from P3. And our first talk will be held by Ethan Self. He's Research and Development Associate at the Oak Ridge National Laboratory. And we're looking forward for the talk of solution-based synthesis of disordered rock cells in lithium-ion cathodes. So, Ethan, the stage is yours.
Thanks, Christoph, and good morning or good evening, everybody. I guess that's the beauty of virtual meetings. So I'm going to just keep my camera on here to show you that I'm a real person. I'm going to turn it off so it doesn't maybe interrupt some of the slide formats before I switch over. So yes, my name's Ethan Self. I'm an electrochemist and staff member in the Energy Storage and Conversion Group at Oak Ridge. And it's my pleasure to share some of our team's ongoing work developing scalable solution-based synthesis platforms for DRX lithium-ion cathodes. Before diving into the technical portion, I want to thank the organizers for the kind invitation and opportunity to share our work with you today. And also want to acknowledge the outstanding contributions from this team, without whom none of the work would be possible. So most of the data that I'll be showing today was acquired by Matthew Chambers, who is an outstanding postdoc, recently left our group. There were also strong support from Max Marcus and Prince, a graduate student, and Beth Armstrong, who is a senior staff member with decades of experience in combustion reactions. So, as I'm sure you're all very well aware, the demand for lithium-ion batteries is continuing to grow every day. We want batteries with more energy, more power, and we want them to be cheaper as well. And so that is driving a lot of supply chain constraints for particularly nickel and cobalt, which are critical resources for the cathode active material. And this is because the highest energy intercalation cathodes are typically layered Rocksalt structures, where you have lithium lithium cations in a specific site and the transition metal cations in a separate crystallographic site. And there's really pretty limited compositional flexibility here. So you have a lot of things such as lithium cobalt oxide, nickel cobalt aluminum, nickel rich NMC. And so the more of these materials that we need, the more that supply chain gets constrained. So to kind of decouple that bottleneck, disordered rock salt materials are compatible with a much wider range of transition metal compositions. So you can attain high energy while using more earth-abundant resources. What I'll be primarily talking about today are manganese titanium-based compositions. So here, manganese is actually the charge compensation redox center, and titanium is in a 4 plus valence state, which helps to stabilize the DRX framework. So now, rather than having this specific crystallographic ordering of different cations, you now have a random distribution of lithium and transition metal cations throughout the structure. So a number of DRX compositions have been developed and explored, especially over the past decade. And while they do show promising energy densities that are competitive with incumbent and established lithium-ion cathodes, there are a number of key challenges that have prevented them from really entering the marketplace. These are pretty widespread, related to synthesis challenges. That's what we'll be mostly focusing on today, but also a number of electrode engineering issues in terms of carbon content and also interfacial coatings that are needed to stabilize the interface. And also some sloping voltage profiles that result from kind of the disordered nature of these active materials. So, of course, don't have time to go through all those today, so I will instead be focusing on the development of scalable synthesis routes. So if you look broadly in the literature, DRX materials are typically prepared through solid state or mechanochemical reactions. So here you take your inorganic precursors, you blend them together in a high energy ball mill for several hours, and then this powder that you obtain after that milling process, a lot of times you go through a second solid state reaction, which is high temperature and long times to produce the final DRX powder. So this is a straightforward synthesis platform. It's been demonstrated for a wide range of chemistries, but it creates some challenges when you start looking at scalability. Because of the intense energy requirements, especially from that initial milling step, this is limited to gram scale quantities. It's really hard to try to do this in kilogram and larger batches that are needed for practically irrelevant applications. And also due to the aggressive kind of mechanical milling nature here, you don't have much control over the final particle morphology. So this has implications in terms of the powder tap density and also the electrode's volumetric energy density. And something else that seems to be that's quite problematic here is a lot of these DRX materials are actually oxyfluorides, and it's quite challenging to incorporate that fluoride anion into the final DRX structure using the solid state route. So to address some of these challenges, our team is developing solution-based combustion reactions. So combustion reactions are readily scalable and are currently used in production of industrial relevant